Okay, guys, we're back, and once again, Ribby, my voice of reason, pointed out that I did not do a very good job going through those PowerPoints. And on the quiz, the HR diagram and life cycle of a star is just too important not to make sure you have all the information you need. First off, this is a picture of an HR diagram. It is called a Hertzsprung-Russell diagram. It was named after two astronomers. But this is not your ordinary graph. This is not a graph like we've been graphing all semester. This one is quite unique. First of all, if you look at the x-axis here, you will see that the temperature, it is in kelvins. That is a little different, but the temperature runs backwards. As in hot is over here on the left-hand side, and cooler stars are over here on the right-hand side. That's number one. Number two, you'll notice the scaling is not your traditional scaling. When it decreases by halves. Okay, so the scaling on this is not linear, it is logarithmic. And then on the luminosity side, now one thing you need to remember is that luminosity is measured in watts. So you're talking about energy per second. So you're talking about the total energy of a star. There is another term called intensity, and that is watts per meters squared. So two stars could have the same intensity, but if one star is larger than the other, it would be significantly more luminous. Now, luminosity is based on two things. Basically, it is based off of the surface temperature and the surface area, which is dependent on diameter and radius. The other thing you need to understand about luminosity is it is an absolute brightness. There are two types of brightness. There's absolute and apparent. Because most of us are never going to leave the Earth, when we look at stars, we see their apparent brightness as seen from Earth. But it is quite possible for two stars to have the exact same luminosity, but one appear brighter to us just simply because it is closer. Take Mr. Sun, for instance. Mr. Sun does not have all that high of a luminosity as far as stars go. However, in our sky, Mr. Sun is always the brightest star because he is so close to us. All right. The other thing you're going to notice about the luminosity axis is that it is very different than something you're used to. It also is logarithmic. If you go here to the number 1, or I could have written it as 10 to the 0 power. Okay? 10 to the 0, anything to the 0 power is 1. Mr. Sun's luminosity is a 1 or a 10 to the 0 power. We use our sun as a reference point. Now, the luminosities are the actual brightness of stars, so the luminosity they actually have regardless of how far away from the Earth they are. Now, as you go up here, 10 to the 2, that would be 100. 10 to the second power, that would be 100. So you would have something that is 100 times more luminous than the sun. And then 10 to the fourth power, 10 to the 6. So you would go 100, 10,000, a million. And then down here, you would be 0.01, 0.0001, and so on. So the stars down here are less luminous than the sun, and the stars up here are more luminous. Now, the bulk of the stars are in this band here. This is called the main sequence band. Stars spend 90% of their lives as a main sequence, and 90% of all the stars you look at in the sky at night are main sequence stars. When main sequence stars exhaust all of their hydrogen, they expand, and depending on their mass, they either turn into supergiants or giants. This is when they start fusing helium. Okay? Now, the reason the giant stars are lower in temperature but still have a really high luminosity is that their surface area is very, very large. So when our sun goes from a main sequence star to a red giant, his core temperature will increase because it has to fuse the helium, but its surface temperature will decrease significantly, but its luminosity will increase because the radius will increase. He will also be a lot less dense in this stage because he will have roughly the same mass that he did when he was a main sequence star, but he will have a much larger volume. Now, supergiants up here, they meet a different fate, but stars the size of our sun, when they exhaust their helium in their core, they then collapse into the white dwarf. And they will collapse into an object that is about the size of the Earth, or about the size of a planet. It will be extremely hot and it will be extremely dense, but it will not be very luminous because it will have a low surface area. So the main sequence band follows the higher temperature, more luminous, lower temperature, less luminous trend. But giants and supergiants and white dwarfs are the exception to that trend. Now, the stars up here on the main sequence band, they are high mass. They burn through their fuel quickly. They have short lives, and they're very luminous. The stars down here are lower mass. They burn through their fuel more slowly, and they have extremely long lives. Now let's take a look at a practice sheet. I kind of want to explain to you how this works. You can kind of go over it on your own. I'm not going to read it to you. But basically, we have a basic HR diagram here. And it says which star has the highest surface temperature. Well, you would go clear over to the left side. And just by a hair, it's A. Just A is a little further to the left than C. All that's checking for is to make sure you understand that the surface temperature is hot on the left side and cooler on the right side. Okay, and I have left a key for you. Couple other important questions. Down here on number 22, it says giant stars have a lower temperature than most main sequence stars. Why are giant stars just as luminous or more luminous than main sequence stars? Well, it's because they have very large surface areas. That really does make the difference. On the next page, it says why aren't neutron stars and black holes on the HR diagram? Well, they're really hot, okay, especially a neutron star, but their surface area is so small that they don't basically have such a small amount of luminosity you can't even put it on the chart. And so the two things that luminosity of a star depends on is your surface temperature and your surface area, or you could also term it as radius or diameter. Now, I do want to review just a little more on the stellar evolution. I've posted some of the other videos that I hope you've watched, explaining pieces of this progression. All stars, regardless of mass, start out in a nebula. Okay. Then they reach what's called a protostar stage, and once their core gets hot enough, they will start fusing hydrogen and they will become a main sequence star. This is where a star will spend the bulk of its life. A star the size of our sun has a 10 billion year lifespan. A more massive star may have 100 million years or less lifespan, and a less massive star could have a 30 billion year lifespan. Okay. After a star the size of sun exhausts its hydrogen, it turns into a red giant. It goes through a little midlife crisis, blows off some outer layers in a planetary nebula, and collapses into a white dwarf. And theoretically, the white dwarf, since it is no longer undergoing fusion, it never replaces its energy, so it is just continually cooling off and would eventually, theoretically, turn into a black dwarf. Now, here's the problem, and here's why I'm saying theoretically. Our universe is only about 14 billion years old. quite frankly, we have not seen any examples of these two things yet. So we don't technically really know what happens because the universe isn't old enough for this to have happened yet. Now, a higher mass star will expand into a red giant or supergiant, and it will explode. It will go supernova, and it will either collapse into a neutron star or a black hole. Okay, I just wanted to give you a little review, especially before you take the quiz. I hope everything else is going well, and I will continue to keep posting lecture videos.